This is the required review for chapter 6 through 11. You'll notice again, it does give you the little formula sheet that you'll be given on the exam. So make sure if you want any other formulas or anything else that you memorize it. First problem, remember our formula, which says that any individual measurement is equal to an exact value plus bias plus chance error. So I want to know what's the difference between bias and chance error. So bias affects all measurements in the same way. So either all the measurements will be too high or all the measurements will be too low. But it affects them all systematically in the same way. Whereas chance error, that's just the pure randomness that happens in life. And that changes from measurement to measurement. Some will be high, some will be low, some are positive, some are negative. Now, just to know, again, we always have chance error. That always happens anytime you're measuring anything. And then there's usually bias as well. Not always bias, sometimes you can get rid of that. But there's always going to be some chance error. So next, a butcher has a scale on which he weighs the meat that his customers buy. In order to increase his profits, he has doctored the scale so the weight of the meat is consistently about 10% more than the actual weight. So this is an example of what? Well, this would be bias because he adds 10% every time. So every time it's 10% higher, so it's very systematic. This would be bias. And then there's something called the Sports Illustrated jinx. This states that whoever appears on the cover of the Sports Illustrated is going to have a poor following year. Now, just in case you don't follow the Sports Illustrated like I don't, just to note that to be on the cover, you have to have had an incredibly good winning streak, a very good year. So what is the statistical phenomenon that could explain this? So what would say that if you have one really, really good year, your next year would probably be worse? That would be the regression effect. The regression effect says most things tend to kind of try and get close to the average. So it says if you have an extremely high result the first time, which is probably just due to luck, then you're likely to get something closer to average the next time. So like even if you're good to get, if you have an extremely good day, it's probably just kind of due to luck there. So the next time you'll probably have a little less luck. You'll probably be a little closer to the average. So all athletes have good games and bad games. A winning streak might be just like a lucky streak, but it's likely to then fall back towards an average performance soon. Okay. Not to counteract like, yes, you can have a good year, you can improve, you can do good things, but the times when you just have a really lucky game and you seem like you're on fire, that's probably due to luck, so next time you might be a little less lucky. See, an engineer at General Motors collects data on the weights in thousands of pounds and the fuel economy in miles per gallon of 37 vehicles and does a scatter diagram. Okay. So we have weight, we have an average in SD, fuel economy has an average in SD, and our correlation. We drew a regression line for miles per gallon on weight. So that means we have weight on the x-axis, and we're going to use that to try and predict miles per gallon. Let's see, so first question, the scatter plot of the data shows what? And it looks like they're trying to figure out how the weight and miles per gallon are related. To answer this question, I like to look at the scatter plot first and try and figure out what it should be. Then I come back and try and pick the answer that matches. You're much more likely to get the right result if you do things like this in this class. Write down your answer first, then look at the choices. Okay, so it seems like when I have low weight, so low weight seems to be high miles per gallon. And if I come over here to high weight, then it looks like I'm at low miles per gallon. Now let's find a matching answer. Let's see, this says there's no relationship between weight and miles per gallon. Well, it looks like there is relationship. I'm not going to say that it's a causal relationship, that one's causing an effect on the other, but they are related somehow. So it can't be that. Let's see, heavier cars tend to have lower gas mileage. So high weight, low mileage, that would be it. Whereas this one said heavier cars are associated with better mileage. Well, the heavy cars have poor mileage, so it's not that one. And lower gas mileage, which would be lower gas mileage with lighter cars. Nope, lower gas mileage is heavier cars. So not that one. let's see, on our scatter diagram, label the point which represents the Chevy Spark. That's a car that weighs 2,200 pounds and has 37.3 miles per gallon with the letter A. So 2,200 pounds, because our units are in thousands of pounds, is 2.2. X equals 2.2. Just a minute, I'm going to restart. My computer's having issues. Okay, so X equals 2.2. That's your weight. And Y equals 37.3. So let's see if we can find that point. So 2.2 is probably about here. We're looking for 37.3. It must be this one. So that's the Chevy Spark. Let's see. On our rough scatter diagram, draw the SD line through the data. Clearly label our point of averages and find the slope of the SD line. So if you remember, our SD line always has to go through the point of averages. Which basically is the average of X for X and the average of Y for the Y value. So let's see. Coming back up to the top of the page, average of X is 2.89 and average of Y is 24.64. Let's see, so 2.89 and 24.64. So 2.89 would be about here. 24.64 be about here. Looks like we're right here. The regression line also goes through the point of averages, so you don't have to be on the line. So that's our point of averages. Let's find the slope. So your slope for your SD line is equal to, we do the SD of Y over SD of X. Now standard deviations are always positive. So this would always be positive, but sometimes you have to have a negative slope so you can go down. So anytime if you know that you have a negative correlation and you know you need a negative slope, you just put a negative right here. So let's see, standard deviation for Y is 6.46 and it's going to be over 0.69. And we said it needs to be negative. Now you can put this into your calculator. I don't actually see the use, but in case you want to, it's going to be negative 9.3623. But it's usually easier to leave things as fractions for slope because you can do rise over run. So we're going to go down 6.46 and we're going to go over 0.69. From our point of averages, so we're going to go down about 6, so somewhere about here, and go over 0.69, so somewhere probably about here, and put our line. Now, this is our SD line. I can't really ask you to do that very easily on the exam, this multiple choice on the computer. But what I can ask you is I can ask you which one is steeper. So you'll notice when you look at this that the SD line does seem to be steeper than the regression line. And that is always the case. And that's the part that you need to actually remember. Is that the SD line is steeper than the regression line. Now, next, the correlation between the weight and gas mileages is R equals negative 0.91. This tells us what? Okay, this is very similar to what we did before. It will probably be on the exam a couple times in different ways like this. If you have negative 0.91, you're kind of going down. And here we had weight. Here we have miles per gallon. Again, do your answer first, then look for the matching choice. So if we have low weight, we have high mileage. So low weight tends to go with high mileage. And high weight, See, high weight looks like it's low mileage. Okay. Let's check our answers now. Heavier cars tend to get more miles per gallon. So heavyweight, more miles. Nope, that would be wrong. Heavier cars tend to get fewer miles per gallon. That looks right. Let's see, 3. There's almost no connection between weight and gas mileage. Well, not that. It seems like they're pretty well related, actually. Let's see, an arithmetic error was made. Correlation has to be greater than 0. Well, that's not right. You can have negative correlation. And 5, the average gas mileage has gone down since last year. Well, we didn't talk anything about years, so that's just kind of silly. Let's see, use the regression method to predict the miles per gallon for the Chevy Spark weighing 2,200 pounds. So in this case, x equals 2.2 because we were using units of thousands of pounds. When we use the regression method, the first thing we do is find z. So z is always equal to x minus the average over the standard deviation. So in our case, x is 2.2 minus the average for the weight, and the average for weight is 2.89 over your standard deviation of 0.69. Putting this into my calculator, I actually get -1. So it is 1 SD below average. Step 2, find R times Z. So R times Z is going to be equal, let's see, R is -0.91, Z is -1, so we get positive 0.91. So the miles per gallon should be 0.91 standard deviations above average. So 3, find the actual y value. So we said it should be 0.91 standard deviations above average. So it should be the average plus 0.91 standard deviations. So let's see what that gives us. The average for miles per gallon is 24.64 plus 0.91 times the standard deviation for the gas mileage is 6.46, which gives me 30.52. So we predict that if it weighs 2,200 pounds, that it will get 30.52 miles per gallon. But how much is our answer likely off by? Well, that always means find one RMS error. RMS error is equal to the square root of 1 minus r squared times the standard deviation of y. So square root of 1 minus, now that 0.91, the negative 0.91 is inside parentheses to square it, times times 6.46, which equals 2.678. So that means we predict it will be 30.52 miles per gallon, give or take 2.678. So we predict 30.52 miles per gallon, give or take 2.678 miles per gallon. Now, would you be surprised at the Chevy Spark's actual miles per gallon given the predicted value? Now, for this, you have to go back to the previous page when it says the actual miles per gallon is 37.3. So would you be surprised about that? Well, we're only surprised at if it's more than 2 RMS errors from the average. Sorry, from the predicted. So let's see what that is. So we predicted 30.52. So if we do plus or minus 2 times the RMS error of 2.678, so we're going to do 30.52 minus 2 times 2.678. And that gives me 25.16. And if I add it instead of minusing it, so we add 2 times 2.678, we get 35.876. Oh, that was 164. Okay, so now is 37.3 in this range? Okay, let's see. So 37.3 is not in that range. So that means it's more than 2 RMS errors away. So that means we are surprised. Let's see, since the Chevy Spark actually gets 37.3 miles per gallon, let's calculate the residual. Now your residual is always equal to your actual minus predicted. So the actual is 37.3. The predicted is 30.52, which gives 6.78. So that's the residual. It's positive, so that means we were above the line. So it has better gas mileage than we were predicting. Right. Let's see, next, our residual plot for the data is below. So what is the appropriate conclusion from this plot? Now, when you look at the residual plot or scatter plot, there's a few things you're looking for. You're looking to see, did the data seem to have constant vertical spread? Is it homoscedastic? You want to see, is there a pattern, or you want to see, are there outliers? Because those are all things that send up red flags. So when I look at this, notice kind of, what do you see? That definitely looks like a pattern. So I would go with number 3 here. The residual plot shows a pattern. So the regression line is probably not a best fit for this data. Even though we went and did all that work, it kind of shows a pattern. So we don't really like that. That pattern is there in the scatter plot if you look very closely, but we didn't really notice it on the scatter plot. It was easier to see on the residual plot. Sometimes that's the case. Okay. J, we're supposed to pick the false statement regarding the data of miles per gallon on weight. So first, the correlation for weight on miles per gallon is R equals -0.91. Now, you might not notice this if you're not paying attention, but basically here they switched miles per gallon and weight. And they're asking, would that change your correlation? Because before we did miles per gallon on weight, now we're doing weight on miles per gallon. So we're using miles per gallon to predict weight. So if you switch your X and Y variables, that does not change your correlation. Okay, so it stays the same, so that's true. Let's see, multiplying all the weights by 1,000 will not change R. That is also true. Adding 50 to all your gas mileages will not change your correlation. That is true. And changing the weight to kilograms will not change your correlation. That would be true. So all of these are true. That's because you'll see how I made a note. Correlation does not change if we switch X and Y. It does not change if you add the same number to each value in either list, so either the X's or Y's, it doesn't matter. It doesn't change if you multiply the same number to each value in either list. And it doesn't change if you change the scale. So like changing from weight to kilograms, that does not change the correlation. Let's try the last one. If we added a car that was 4,000 pounds and got 30 miles to the gallon to the data set, would our correlation get stronger? So if you remember, our data plot looked like this. You can flip back to your previous page. And so if I was to look for something that has 4,000 pounds and 30 miles to the gallon, 4,000 pounds, 30 miles to the gallon, that's up here. That's the point that they want us to add. Well, this would be an outlier, and outliers change correlation if we added that. It's going to change the correlation quite a bit if we add it. So it's up here, that would change our correlation. So this one is false because it said our correlation would get stronger, but if it's an outlier, the correlation is going to get very weak. It's going to get very small. So that last one was false. John looks at this study and says, if we focus on lightening cars, the gas mileage will have to improve. So what does statistics say? Well, statistics says that lighter cars do seem to be associated with better gas mileage, but it's not going to let us say a cause and effect, okay? Because one thing we want you to memorize, correlation is not causation. We can't say if it's associated as cause and effect, and we can't say if it's correlated as cause and effect. Association and correlation mean fairly similar things, but correlation is like an actual number that we find for linear regression specifically. Okay. So even though it seems like it would be true, we can't say cause and effect with statistics when we do a linear regression like this, because usually it's an observational study, and so we can't say cause and effect. You can think about it as maybe they lightened the cars by taking out the engine. That's probably not going to make your miles per gallon better. Or maybe they have to cut corners some other way. So just truly lightening it is not necessarily going to make your miles per gallon better. Here are some scatter diagrams. Match each scatter diagram to your correlation. The easiest thing for me to do is first look through and see which ones are positive or negative. So like this first one is positive, this next one is negative, negative, positive. Okay. Now look at your two positives. Which one is bigger, or like which one is stronger? So this one seems to be much closer to a line. So let's look for the high positive. So it's probably going to be R equals 0.7. Whereas this one seems like it's very loosely correlated. So let's go with a small positive of 0.16. Okay, up here, this one is very tight to the line, so let's go with R equals negative 0.82. And this one seems to be very loose and not close to the line, so that would be R equals negative 0.37. So that's how I like to do it. And last question. Here are some scatter plots with the corresponding residual plots for 4 data sets. Which one should you use linear regression for? So remember, we're looking for 3 things. We want to check, is there a pattern? Is our vertical spread about the same? And do we have an outlier? So let's actually skip set 1 for a second. Let's go to set 2. Notice it looks like we'd have a pretty good thing. It looks like it's a straight line. Okay, that's pretty good. For residuals, looks like we have fairly constant spread. If I was to draw my lines, it's fairly constant. But look at that outlier. And so we don't want to do it with that outlier, so that one's going to be a no. Okay, set 3, when I look at it right away, I see that there's a pattern here. The shape, you can see a shape in the residual plot, you can see a shape in the scatter plot. It's not a line pattern. So it has a pattern that's not a line, so this would be no. Set 4, notice how it kind of goes like this. That's a sign that you don't have that homoscedasticity that we want. Because if I look at the vertical spread, it's big, medium, shrinking, shrinking, tiny, 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 tiny. So the vertical spread changes. That means it is what we call heteroscedastic. And so we can't do linear regression. So finally, coming back to our first one, it looks like a line would fit that. It looks like it's that nice football shape. I don't see any outliers. If I kind of check that vertical spread, I mean, it's not exactly the same, but that's just because we have a small data set. I don't see any like huge patterns that it's changing. So it looks just fine.